Hello, welcome you all for another session of this lesson. In my career of flying, which spanned over 30 years, I've had 4 in-flight shutdown procedures. Some of them forced and some of them deliberately done by myself. The last one being when I was flying in the airline. I was flying on a small route from Chennai to Bangalore with full passengers, and as we reached the cruise level, we had to carry out an in-flight shutdown. It was a precautionary shutdown, of course, and yeah, the point which I want to drive at is that in-flight shutdown situations are not very uncommon, and so that takes us to this lesson of Enroute procedures. Let's go to the lesson. Get on to the lesson. In this series of performance lessons, we learned we introduce ourselves to the speeds, the takeoff weights, and some runway issues. And then we graduated on to the takeoff performance per se, and then we learned on segment climb. Also, we learned that the segment climb ends at 1500 feet AGL. Now let's recap. The aircraft climbed to 1500 feet AGL, and it reached a point called the 10 minutes point where the live engine thrust was kept at the maximum takeoff value, which has of course got a limitation of 10 minutes in most aircraft. So at that 10-minute point, the aircraft has changed over the thrust to max takeoff to max continuous thrust, and it has been maintaining the speed, best lift by drag speed or best climb speed, so as to reach this height of 1500 feet. Now, two scenarios are possible. If the departure weather of the airport from which the pilot departed, if it was within his landing minima, then he has an option to divert back to the departure airport itself. But if it is not within minima, he has to divert to an appropriate airport. We will see that as we go on to the lesson. Okay, let's see some legal requirements. The legal requirements prescribe that when the landing requirements at the departure airport is not met for meteorological or performance reasons, it is necessary to plan a takeoff as an alternate takeoff alternate airport, which shall be located within 1 hour flying time at a single engine inoperative still air speed for a 2-engine aircraft. I hope that is very self-explanatory. That means we take the normal cruise speed on a single engine, and we have to have a diversion airport at the when we depart, in which the performance and the weather criteria would be within limits, within your minima. Then only you can depart an airport. So that's the rule, covers it all. So the pilot, in case he is not able to divert back to the place of departure, he has to divert to the alternate airport where all conditions will be met, since the rule prescribes that he couldn't have taken off otherwise. In an airline, every route would have been studied in great detail for the appropriate type of aircraft and its performance. So, planning a route starts with a detailed study of route study. In that, they would have studied the terrain, the en route obstacles, the route safety altitudes, the minimum obstacle clearance altitudes, and en route altitudes and alternate availabilities, alternate airports, suitable alternate airport availability for the appropriate type of aircraft, and destination minima, which is a detailed study of the route is always precedes any route planning, without which they may not get the legal permission to operate the route. Anyway, to summarize from this lesson point of view, a detailed route study is carried out for the aircraft performance en route for several failures before planning the route and the route procedures. Okay, let's see the rule position regarding en route alternates. As you can see, when we plan a route, so the 60-minute rule states that an operator shall not operate a two-engined aeroplane over a route which contains a point further from an adequate aerodrome than the distance flown in 60 minutes at the approved one-engine inoperative cruise speed. Okay, it simply means that at any point on the route, if you were to suffer an engine failure, you should have an en route alternate within 1 hour or 60 minutes flying time from that point to divert. So at any point you should be able to divert to an alternate airport, which is the requirement as per the legalities. So when an operator plans a route, he would have planned it with this only in mind. Of course, there are other provisions like extended timing for the 60 minutes rule, which we shall see in a separate lesson. Let's proceed further. Let's see the different scenarios. Now let's take the scenario where the aircraft completed the segment climb and it reached 1,500 feet AGL, and of course it's on a single engine. Now, if for some reason diversion back to the departure airport is not possible, then the pilot would have changed over the thrust setting to max continuous thrust, and he would be maintaining the best climb speed, or the best lift by drag ratio speed, or in some aircraft it's called a green dot speed, and he will continue to climb to the safest altitude which meets all terrain clearance and divert to the airport within 1 hour flying time of single engine cruise speed. So that's very clear what happens immediately after takeoff if there was an engine failure and if the departure airport weather minima is not within the pilot's minima. Let us take an en route scenario. Let's assume that the aircraft is cruising on a route at a very high altitude. Now it suffers an engine failure scenario. Now there would, as per the flight manual, there would be some actions prescribed to secure the engine and change over to the max continuous thrust settings, and then there would be speeds which are prescribed. Now the best course of action that the pilot would take is to get onto the green dot speed, that is the best lift by drag speed, in which he will have the least rate of descent let's appreciate at a high altitude, it's not climb anymore, it is descent. We must appreciate that this single engine cruise altitude is somewhere in between lower, mid-level altitudes. Therefore, if you are at a lower altitude, as it was happening on a takeoff scenario, you would be climbing. And in an en route scenario, where the altitude has been very high, even with the best lift by drag ratio speed, the aircraft will gradually continue to descend and reach the altitude which is appropriate for that all of weight on a single engine. So that's what will happen on an en route. With an engine failure, the pilot, after securing the engine, he will change over to max continuous thrust, get on to a prescribed speed depending on the route, and then drift down to the drift down altitude or en route net, gross or net, which we shall see. So he would be drifting down to an appropriate altitude. That's the point which at this point we need to understand. Okay, let's a little bit discuss this en route procedures and strategies in a little bit more detail so that we will develop a better understanding. Practically, and in many aircraft as prescribed by the AFM also, there are two scenarios which are possible depending on the route. If it was a plain and a simple route without much obstructions, then there is a different requirement. And if it was a route with on a hilly terrain or very high obstructions, then it requires a different strategy. Why? Let's appreciate if you have had an engine failure, the first aim is to quickly land in a place to secure the aircraft and passengers, and etc. So, and in most cases, this best L by D or the best climb speed which we are talking about is at a very at a low end of the range of speeds which are possible. It's at a very low speed. So it is going to take much longer to cover the distance on a best lift by drag speed. However, the rate of descent would be so low to clear all the terrain which are possible. So let's discuss these two scenarios. One is if there was not much of high terrain or obstacles, then after securing the engine and changing out to max continuous thrust on the live engine, the AFM will prescribe a speed of a cruise speed, normally about 0.78 Mach, and quickly drift down to the route safety altitude, because by then the flight management system or the pilots themselves would be able to calculate as to what's the appropriate altitude for that all of weight, and what is the approximate drift down route altitude, and of course if it is going to meet the route safety altitude requirements. Now then once you drift down quickly, you are also covering good distance because you are maintaining good speed, and now you are changing out to something called long range cruise speed and then diverting to the nearest airport. Of course, if the route contains very high obstacles which are not meeting the legal requirements of obstacle clearance altitudes, then the pilot would, after securing the engine, will maintain the best lift by drag or best climb speed to drift down as low as possible till he clears the point of high obstruction, and then quickly change over to another profile. Okay, let me introduce you to the gross drift down and the net drift down altitude. Very similar to what we saw in gross takeoff and net takeoff flight path. So let's see the legal requirements. The gross drift down altitude for an Enroute configuration, it must be determined for each weight, altitude and temperature. The variations of weight along with flight path accounting for the progressive consumption of fuel by the operating engine may be included in computation. The flight path must be determined at any selected speed with the most unfavorable center of gravity and the critical engine inoperative. What the rule simply means that the aircraft manufacturer should publish the graphs for such drift down profiles for every all of weight that is possible and every ambient temperature that is possible, so that the pilot is able to calculate the required altitudes at any point or for any scenario. That's what it means. So you will find that aircraft manufacturers publish these graphs. Especially there will be an Enroute segment in the performance graphs. So that's what is gross. And what is the difference between gross and net? We will see later. See the gross drift down and the net drift down altitude. Gross, as we know that it is almost the demonstrated and in the ideal conditions by the test pilot. Generally the aircraft would be able to meet, generally the fleet will be able to meet the requirements of gross performance. And the net performance accounts for any variations in pilot techniques or some other variations in accurate parameters, etc. Anyway, as regards to gross drift down and net drift down altitude, the net drift down altitude is the gross gradient subtracted with a penalty. In case of two engine aircraft or one engine failure, is the gross performance is diminished by 1.1%. That's what is net performance. So all your performance requirements that need to be met as far as the legal requirements are concerned is the net performance, because the gross performance requirements are a little bit higher, and net performance will be much more conservative in our calculations. I just worked out a small calculation so that you can understand. Suppose if the gross drift down altitude were to be 10,000 feet, when diminished by 1.1%, it would be 110 feet, and the net drift down altitude will be 9890 feet. So I hope that makes it very clear. So 9890 is a more conservative figure than that at 10,000 feet, though the difference is marginal at this range. You must appreciate if at 20,000, 1.1% will result in much higher difference. Having seen the net drift down altitude, let's see the legal requirements as far as the lateral limits are concerned. The net takeoff, net flight path must permit the aeroplane to continue the flight from the cruising altitude to an aerodrome where landing can be made, clearing all terrain and obstacles along the route within 9.3 kilometers or 5 nautical miles on either side of the intended track. And an operator must increase the width margins to 10 nautical miles if for some reason, if the navigation accuracy does not meet the 95% containment level. There is a flight management system of the aircraft, and there are some navigation systems like GPS and inertial nav systems, which is expected to keep the aircraft within the prescribed path or the route. So, as long as the accuracy requirements are more than 95%, then this 5 nautical mile terrain clearance can be accepted. But the moment it deteriorates less than 95, that means the accuracy is less than 95%, which there will be a warning in the cockpit through the FMS to the pilot. Then he must switch over to the clearance requirements that extend to 10 nautical miles on either side of the route. That's what the rule says. Let's go down to the actual terrain clearance requirements. The gradient of the net flight path must be positive at least 1,000 feet above all terrain and obstructions along the Enroute segment. What it means is that at any time, if there was a drift down due to a single engine, that net drift down altitude must clear all the obstacles by 1,000 feet on the route. That's what it means. Let's discuss this provision in a little bit detail. The rule position says that the net drift down altitude must clear all the obstructions on the route by 1,000 feet. That is to be calculated for the worst, that means the maximum wall of weight, the worst and the most adverse weather conditions, and you calculate what is going to be the drift down altitude, derive a net drift down altitude and compare it with the highest obstructions on the route. And if it is going to meet the 1,000 feet requirement, then you accept the route. But this may not be practical at times, because sometimes the routes are very longer, and maybe if the obstacle was located farther away, then maybe it was meeting the obstacle clearance requirements. Anyway, since the rule position has defined the requirements, it has given an alternate provision also. That means there is another 2,000 feet rule. It can meet the 2,000 feet requirements if you are not able to meet the 1,000 feet requirements. The details of 2,000 feet requirement is what we will see in the next few minutes. Then we will be able to appreciate the difference between these two. To explain once again, the 1,000 feet requirement is for the entire route. That means you just calculate one net drift down altitude for the worst possible scenario, and you take the highest obstruction and see if it is going to meet the requirement, irrespective of you are going to encounter the situation practically or no. So, for which this alternate of 2,000 feet rule has been prescribed. Okay, let's go through it in detail, and I want you to study the slide also in detail. I have shown 2 points, point A and point B, and the That is, the aircraft is cruising, and if it were to suffer an engine failure before point A, so at any point it's able to drift down uh, and the net drift down path is able to clear the obstacle which it has already crossed uh, by 2000 feet. That's from point A. And of course, from A, it is able to continue and drift down and proceed on the route as well. That means both the scenarios for returning back to the departure airport and continuing on the route, it is possible for the airplane to meet the legal requirements of 2000. Similarly, from point B, that obviously that from point B, it is able to up to point B. Anytime after point B, if it is able to, if it is suffering an engine failure, it's still able to meet the requirements of 2000 feet net drift down path and proceed on the route. From the picture, I'm sure it is very clear of the scenarios of point A and point B. Okay, let's see another scenario as I've shown in the picture. Now the point A and point B are slightly different, and I want you to notice. That means up to point A, you are able to return back to the departure base on a single engine, maintaining the 2000 feet clearance. Obviously, after A, you are not able to proceed on the route because you are not able to meet the requirements of an obstacle which is lying ahead of the flight path. Similarly, so that point from which it can clear is the point B. That means up to point B, between A and B, you are not able to clear the route or you are not able to meet the requirements of obstacle clearance which is ahead in your route. Of course, after point B, you are able to continue on the route. So what's the big deal? So let's see the deal. What happens between point A and B, where the terrain clearance requirements may not be met? So that's where there are legal provisions. Between A and B, the legal provisions provide for planning alternates for that particular segment, planning a diversion or other measures such as dumping fuel if it is possible and prescribed by the aircraft manufacturer, and or reduce the all of weight, etc. So legally it is provided to fly this route. For flying this route and not if the obstacle clearance between these point A and point B is not being met, the operator can plan alternate devices, alternate measures to meet the requirements. He can plan a diversion, en route diversion if the diversion route meets other legal requirements, and as long as he can satisfy the legal authorities, he can plan the route. So for long routes and for some tricky where high terrains are existing, the operator is not constrained legally, so he can go ahead and plan such routes. So that's what is the requirement or the provision which has been created by this 2000 feet rule. I hope I made the difference very clear. In a 1000 feet rule, it's one uniform, one highest obstruction and one drift down altitude, net drift down altitude, which has to meet the legal requirement of 1000 feet clearance. In this 2000 feet rule, it can be segment wise, it can be calculated, and the operator can satisfy the legal authorities that he is able to plan the route for any eventuality. Then it will meet the requirements. Okay, I hope you enjoyed going through this lesson on en route performance. Of course, it's just an introduction, and as you young pilots keep flying, you will encounter several situations, several routes, and you will find the calculations and flying these routes very, very interesting in your career. So the legal requirements will keep changing, and depending on different scenarios, depending on different commercial requirements. Therefore, it's a very interesting subject which you are going to keep encountering, and you are going to keep enjoying this subject. And thank you all for going through this lesson. As usual, please feel free to offer your comments on the email ID given below. Please offer your critical comments so that we can produce improved lessons in a more professional manner. If there are some points to be amplified, then again I will request you all to drop in a mail so that we can improve on those in our next version of these lessons. We are sure going to publish much more professional versions of these lessons in the days to come. Thank you all once again.